Alright, in this lesson we revisited some of the equations that had come up in the previous activities about projectile motion. So I'm going to spend a few minutes talking about that here. First off, I want to make sure you understand these are all the equations that we've been using so far this year when we've talked about acceleration, speed, and velocity, and so forth. Even though it seems to you like you've seen a whole lot of brand new equations these last couple days in projectile motion, you haven't. They're just variations of these. So modifying these equations slightly, these kinematic equations, so that they work for projectile motion. Before we get into that, let's take a second just to think about the idea of the horizontal motion. So remember that you have got a vector, and in these examples there's going to be a velocity vector. And very often it's going to be going off at an angle like that, slightly up into the air, so up and forward. This vector has got two components, a horizontal component and a vertical component. Sometimes the object isn't launched straight up into the air, sometimes it's launched just this way, like an object is pushed off of a table. It only has an X component. This object is going to follow a path kind of like that, and I'm sorry, I know that's messy. This object is going to follow a path kind of like that. They're both projectile motion. In both of them, there's first and foremost, one thing that's critical to understand about the horizontal velocity, and that's that it doesn't change. So as the object is traveling this trajectory, it is neither speeding up or slowing down in the X direction. Same thing here. So velocity in the X direction is equal to the velocity in the X direction original, so at the beginning of the problem, which is equal to velocity original times cosine theta. This is the equation as we learned it back in the day in our kinematic equations when we were in one-dimensional motion. This red version over here, and the rest of this lesson will be color-coded like this, is the same equation, this equation right here. It's the same equation, but this time it's been totally tricked out with all the symbols and names and words that we would use while discussing projectile motion. And this green one is kind of in the middle. In other words, we're not just talking about velocity, we're talking about velocity in the X direction. In projectile motion, we refer to the distance in the X direction as X, and time is time. Now I've taken one step farther, and I've worked my trig component of my equation right into the equation itself. So Vx is equal to VO cosine theta. That's this right here. Alright, so if we were going to use SOHCAHTOA to find it, that's how we'd find it. And the word that we use in projectile motion to talk about how far the object travels in total in the X direction is often called the range. Now when you think about it, this is actually a pretty basic equation. This equation right here is pretty straightforward. We're going to use this a lot. So it's nice that something you use a lot is pretty basic. And it's basic because, again, there's no change in the velocity in the X direction. Alright, now let's take a look at vertical. Here are the three kinematic equations, the way that you learned them back in the day. And we're going to break them up into my color-coded way of looking at them. Here it is, VF equals VI plus AT. And here it is totally tricked out in red, which means that I've made all the substitutions that you would make when you would be thinking about projectile motion. And here it is in the middle. So let's take this one to focus at it. The velocity in the y direction at any particular point in time is equal to the initial y velocity minus g times t. Right? So in other words, as it's moving, the initial y velocity is going to be modified by gt. The negative sign here is taking into account the fact that it's moving and also that g is often negative in this situation. However, I will want to warn you, you don't want to just be plugging in negatives and positives kind of willy-nilly. You want to actually be thinking about it in each step. Okay, what's happening here? Is the object speeding up or slowing down? So, should I be taking away velocity, or should I be giving velocity and making the velocity greater and greater? In this situation, like so, the y velocity is getting greater and is getting smaller and smaller and smaller. So in other words, gravity is working against the y component of the velocity. Slower and slower and slower, comes to a stop, and now the y component of the velocity continues to speed up. In these particular types of problems, like when the object's pushed off the table, the y velocity component is just increasing until it hits the ground. Alright, distance equals VIT plus 1/2 AT squared. Here we're calling our distance y. It's equal to our original y component of the velocity times t minus 1/2 gt squared. So I'm substituting in all of these g for a. So if we're on Earth, 9.80 meters per second squared. And here all I've done is gone that last little step and I've worked my trig function into the equation itself. So original velocity in the y direction is equal to original velocity times sine theta. And here is one last equation that you recognize. Vf squared equals Vi squared plus 2AD. Here it is with the total substitutions for the trig. And what we're really saying is the final velocity in the y direction is equal to the initial squared, is equal to the initial velocity in the y direction minus 2g y, again y being here the distance that's been traveled. Alright, and the important thing here, if you're trying to do the trig while you solve it, make sure that you multiply the initial velocity times sine of theta before you square it. Alright, let's think about what some of these things mean here. Time. Alright, if you're solving one of these problems for time and the problem is over, that means we've solved from here until here. Well, this is kind of like half of one of these problems. I realize that's messy, but I'm sure you can see it's just the downward part of this arc. Right? When you're solving for time for this problem, you want to be thinking about, did I just solve for that time, or did I just solve for the entire time? In other words, you could take this equation right here. Alright? Let's put a little circle on that. You could take that equation right there. And you could talk about this type of problem where an object is being kicked or shot or launched. And you could say, well, you know what? Right here, my velocity in the y direction is 0. You could put a 0 here. You could solve this problem then for time. That time only takes you halfway through the problem. If you want to know the time for the entire problem, you'd have to multiply your answer for time by 2. And we will be doing this later on in class. Or you could be looking at this equation right here, and you could say, alright, I don't want to do just the half the problem, I want to do the entire problem from here to here. What's my change in my, what is my y here? What's my distance in the y direction? Well, if I'm doing the entire problem, y is going to be equal to 0. So you could set that equal to 0, and you could solve then for time. Looking back at this one up here, now whatever I said about this equation with this problem is not going to be true for this problem. Now my Vy is not going to be equal to 0. My Vo is going to be here, and it's equal to 0. And then my Vy is going to have a value to it. Alright, moving on. Again, we're going to use all these later. I'm just talking a little bit about them today. Let's talk about some problem solving strategies. Alright, count on having to find time. Somewhere in these problems you're probably going to have to find time. That's just all there is to it. Realize the difference again between time for this type of problem and this type of problem. And when you solve this kind of problem, make sure you know if you're solving for the time for half of the problem or the time for the entire problem. And when you're solving these types of problems, realize the difference between, again, the time it takes to reach here and the time it takes to reach here. And make sure you realize the difference between the y value for right here and the y value for right here. The y value for right here is going to be the total height. How high does the object go? The y value here at the end of the problem is going to be equal to 0. Alright, now, at some point in time, you are probably going to use this equation. Right? And these here, these should be subscripts. There we go. Sometime during the course of a problem, you're going to have to probably use this equation. It's a pretty easy equation, so that's no big deal. Alright, after we finish this in class, we're going to start doing some problem solving.